So our next speaker is Alexey Kaplan from Columbia University.
Well, we tend to think about us as being not exactly from Columbia University, but Lamont-Doherty or the Observatory. I work on things I'm going to talk about with Doug Chen and Mark Kane. Mark is semi-retired. Doug is director of large group or institute in China, but we keep working together, and I'll say what that brings. Do I point it somewhere? Right. Yeah, but just somehow it is. Right. But where do I need to direct it somewhere? Because it doesn't seem to be jumping. PDF file, right? Yeah. Okay, it works. I should apply more pressure. Yeah. Okay. Right. So. Right. Our group in LDO use an intermediate coupled model to produce so-called LDO5 ENSO forecasts, a part of monthly RI forecast plume, which includes that plume includes about 40 different models. Most of them are GCMs, some of them are purely statistical models. I believe there is one or two intermediate models as well. Talking about intermediate model, it's based on a regional Zebyak-Kane model, which is known for having produced first ever forecast of a linear event of 1986. They did it 9 months before its peak. And this model is called intermediate because it's no GCM. It's actually two linear models. The model only models anomalies and so deviation from assumed mean state. And it has a one mode linear ocean, tropical ocean, and one mode tropical atmosphere, also linear. But interaction between them is non-linear. And somehow that captures large part of the development of ENSO events and proved useful both for research and for practical forecasting as well. So assimilation into this model, which we do because we need to initialize it for monthly coupled forecasts of development of ENSO state. It's also simple. Monthly observations of SST, surface winds, and thermocline depths are nudged in the coupled model as it runs towards the forecast initialization time. And at that initialization time, it starts running without assimilation as a coupled model. However, little sophistication is that thermocline depths are not direct observations. They obtain the actual state of ocean component of this model, into which we assimilate altimetry data, having that, forcing this model with winds, with observed winds, we force ocean component and assimilate the altimetry. Its state is viewed as a approximation of as good for that coupled model as observations, because it's more like it's things it understands. Forecast preparation at the end of each month includes obtaining the last month's means by averaging the incomplete set of available observations to approximate the month's mean. And discontinuation of NSEP-OI weekly quarter degree product early in 2023 gave us a lot of grief. I learned from people here that it's been long. It had it going for a long time, and it was supposed to close, but still it was product which existed almost for 40 years. But suddenly it closed, and we started thinking what to replace it with for observations of SST, so to say. And and many people, I understand, basically switching to NCDC daily or OSST version 2.1 is considered a more or less standard thing. So that's what we did. And then I learned interesting things that final daily fields have of that product has 15-day latency, during which we can use preliminary fields. And that's what we are doing because we need because we have deadlines by which the forecast should be produced. It's somewhere near the end of the month. Sometimes it's before and sometimes after, but full things do not exist. Just before I proceed, let me say that I imagine that all talks before me about couple data assimilation was about real GCM, so you might think that I'm just taking your time about doing silly things. But in fact, model being that simple, and on the other hand, capturing something important about ocean dynamics, allows to do different things. Doug Chen made significant improvements to it. And at that time, in 2004, he showed the set of retrospective forecasts in which model successfully predicted at least basically 6 largest El Nino events, being initialized just by historical analysis of sea surface temperature up to this point, which I thought it was interesting, and that is the version of the model which we use for monthly, so to say, operational forecasts. And I mentioned this plume, IRI plume. These are all different models and different forecasts. And there were, from time to time, people are unhappy that we are taking place in that plume with such trivial model. And there was a bit of argument about that particular time when everybody was going towards El Nino with different strengths, and only we were going to, were showing that Nino 3.4 index would become negative. And we were criticized, but what do you know? These are actually a year after. That's how observations went. They went like that, meeting our model, and that was only one of them. Only one model who actually went that way. That doesn't happen all the time, though. I decided to look how, when we initialize now this model, we are taking about half a month of final fields of OSST to 1, and half of them preliminary fields. How they are different? Daily fields are quite different, but you would hope that when you average for a month, it would differences would be not so large. So this is difference of months. Two monthly averages for July 2023. One is all final fields, and another preliminary fields which existed at the end of the month. I mean, half of them preliminary. And these are differences, and scale goes from -0.7 to 0.7. It's more negative than positive. But I have to say that is of differences that happens. I show this July 2023, and these are global RMS differences. And as you can see, I picked up the worst months to demonstrate the differences. But there is almost as large differences in May, and others are not completely negligible. Global RMS of 0.2, 0.3. If you look at the structure of what happens, these are difference of this preliminary, averaging with preliminary and averaging final of zonal means, going again from March 2023 to April of this year. And you can see that it's, I mean, these differences which come out because of not all data is available, happily change signs. And what would be good to understand what is the structure of that. And that was zonal means difference in zonal means, and this is zonal RMS difference. zonally averaged RMS difference. And you can see also that, I mean, 0.5 is not so rare. Sometimes it's 1 RMS difference for at that latitude. Now, does it matter? Interesting thing, though, that in this, I wrote here that structure changes, but equatorial minimum plots I showed before, there were less differences on equator. And but so when we start forecast, we really index which people mostly predict and among other things and report and compare is NINA 3.4. It almost doesn't see the difference. And this on the left is what forecast for this period. So black are these observations of preliminary thing. No, of actual thing, and red, which you cannot see really because it's very close, is from preliminary one. So in shown is index NINA 3.4. There are no differences, so to say. But these are preliminary forecasts starting from preliminary state, and this is starting from on the right greens. What if we had totally final fields? And if one looks attentively, you could see that forecast with green are actually much better. See that thin line of agreeing forecasts at different lags going right where observations were. That's much more diffused here. And here for the visual pleasure, these two things put together. And again, I proclaim that somehow over this year, final fields were giving better forecasts. And here are basically differences between predicted and actual fields, which you obtained starting from partly preliminary months or full final fields. And as you can see, just like it was always taught to us in chaos theory, you start from almost no differences, and then they grow over the year, and then spread between. So it is possible that starting from two very close fields, you end up with NINA 3.4 in a year of -1, and from the same vicinity, you end up at 0.5 in this particular example, which is pretty small. It's just a year. So my conclusions are that differences between preliminary and final OISST version 2.1 are visible even in monthly means. I hope that wouldn't be the case with 50% of preliminary daily fields. Even though differences near equator are not noticeable, the differences in the tropical monthly mean SST seems to be affecting our ENSO forecasts, at least with this model. It would be interesting to understand reasons for the observed global patterns of differences between SST fields. I wonder if anybody studies that. And it would be particularly interesting to try to figure out how this small differences in tropical indices, but larger in the domain, are affecting our ENSO forecast. Perhaps we could figure out what's the dynamic of their growth, and perhaps some smart filtering of initial conditions would be possible. Thank you.
Questions? Yes.
Hi, Veronica Lance, NOAA. Could you, so you want latency as close to when you do your prediction as possible, right? But your study, excuse me, I was just catching on, you went back and took the final observations and then did your comparison from the, okay. So the closer you got, gave you a better ENSO prediction. So you want closer latency. So what is your time? What's the cutoff? 1 week? 1 day? What? I mean, when do you need the data?
Thank you. I would like to have everything final, but if it can be not 15 days, but 7, I will have just a quarter of preliminary. They're all leaving aside from, I just cannot throw the feelings that perhaps one could figure out, statistically, how after many cases of, after many years, we would have preliminary fields and final fields. Maybe there is a way to figure out what finals should be from preliminary.
And there, of course, the closer to near real time you get, the more uncertainty there is. So it's an optimizing, how certain are you as the time goes on?
I didn't get what you say about closer to what I get.
To the near real time. If you have a very short latency, your data are messier, right?
No, if I have short latency, then my data
the SST data are messier.
No more questions? No questions online? Well, thank you again.
Thank you.
So it was our last speaker of this morning's session. So Erica, what should we do now?
So now we have just an open discussion. If anyone has any questions or comments from the whole session, essentially. And if I can start, I have a comment from Helen Beggs from the Bureau of Meteorology online. She's sleeping now, so I will read on her behalf. She wrote in the chat, and this response are the words of Pavel Sakov, who is the Bureau of Meteorology's ocean data assimilation expert. So she is responding to the question that was given to Mark relating to why do ocean model DA systems thin or superobe the satellite SST observations, reducing the number of observations by superobbing in the Bureau of Meteorology's ENKFC DA system is needed only for reducing the footprint of DA in memory as well as the computational time, which both scale linearly with the number of obs when it is very large. There is only so much information of a particular type that can be uptaken by a DA system. Trying to fit stronger leads to overfitting. The overfitting manifests in larger imbalances and hence increased shock in the model. Therefore, it has strong negative impact on the continuity of the system trajectory. In practice, at some point, it leads to increasing the magnitude of the forecast innovations. And most DA systems overfit because they use the forecast innovation as a metric. They exploit the fact that in the course of overfitting, the forecast innovations are nearly flat or even keep improving marginally at a point when the quality of unobserved fields already dives down sharply. I hope that was a comment. That was a response to the question that Mark had relating to why do ocean model data simulation systems thin or superob the satellite SST observations. I thought I would put that out there since she is sleeping, and yeah, so. Okay, right. Go ahead.
So I think I am confused, but so let me ask this question. So is the implication of the thinning relative to the pixel size on the satellite. If you in fact have a 50-kilometer pixel size, would you in fact still thin? Because at that point you would still have the correlation problem that Sergey was talking about. Am I correct? So you would still have to thin. So there must then be an optimal pixel size at which you would be able to thin, get rid of your correlation, but still have enough data to, in fact, have a successful model. My logic correct in that?
Well, I think that we never know well what is the actual correlations, what is the size of it. So we suppose that 50 kilometers should somehow work well, and within this grid cell of 50 kilometers, we just choose one observation, which is a median value of it. So it's also arbitrary choice, right? We take one observation, which passed the background quality control, and this observation should be a good one, and we only keep one of each type of observations. But it's like a fundamental problem of data assimilation of at which extent they are correlated. Well, the practical thing is that people do thinning normally.
Right, because you don't want to overfit your model. But if you had I guess my question is, if you had you're using the median across your grid scale, right? And if you only had one point, so your observation was 50, it was a 50-kilometer pixel, you would then not be using your median. I would assume that that would not be a satisfactory solution. Correct? No?
Well, yes, probably. Well, I don't know. Maybe Mark, you can comment on that, or?
Yeah, I think in the case of the SST analysis, I don't think we have any observations with such a large footprint size. It's more like 20 kilometers or something like that. I'm not sure. I think there's many experts in the room regarding like AMSR2 observations. I think it's finer scale than 50. In our sea ice analysis system, one of the slides that I showed, we have 50-kilometer, even larger footprint. That's the SSMIS and ASCAT observations. And in that situation, we also have probably a problem of horizontal observation error correlations. But for sea ice, what's really important in sea ice analyses is getting the ice edge correct. So there, even if there's some observation error correlation, the signal itself, the sea ice concentration field itself can go from 100% to near 0% over very short distances. So there, the sort of compromise, the trade-off is we don't thin the observations for sea ice analysis. But SST is probably different. In most cases, you don't have such sharp spatial gradients. And so the issue of not thinning, we could also not thin the observations, but what we would have to do to avoid swamping the system with that, with a particular type of observation, is we would have to overall decrease the weight we give to that, the influence that we allow that type of observation to have in the analysis to sort of counteract, because what happens when you have the correlated observation error, you tend to, and if you don't account for it in the assimilation, what you're doing is giving too much weight to the large scales of the observation. And you don't, and that's why we can thin and we still resolve the large scales. But if we don't thin, then we're giving way too much weight to the large scales, and we have to decrease overall the weight given to the observations. So essentially we're down weighting any information coming from the small scales. So it sort of works out to be almost the same. So if we could correctly account for the error correlations in the analysis, we could get the best of both worlds. We could get the correct weight or influence on the large scales and the small scales simultaneously. But it's really a question of how you're allowing large scale versus small scale information from the observations influence the analysis. And by not accounting for the error correlations, we give too much weight to the large scale and not enough to the small scale.
Thank you, Mark. We have a question online from Christopher.
Hello. I want to comment on this discussion. Thank you for the discussion. It's very interesting on the correlation length scale issue. I think it's worth understanding where the correlation of errors in SST products comes from. It's not really to do with pixel size intrinsically, unless there's an instrumental aspect to that, but generally not. It's to do with the nature of the way in which sea surface temperature is estimated. And generally, the atmospheric correction, to use the old terminology, or the way in which the atmosphere is estimated if you're doing an optimal estimation retrieval, from one SST location to the next SST location will have some correlation in it. And it's really the length scales of decorrelation of your atmospheric estimate, whether explicit or implicit, in your SST retrieval that we have to look at to understand what the appropriate correlation length scales would be. And that's a perfectly doable problem. And there have been some preliminary calculations of that in the past. And it's really interesting that it's now a topic of discussion because those calculations weren't taken up in the past, and maybe it's time to revisit that. I think John Mittaz earlier mentioned that he's done some work on that in the past, and I work with John in Reading, and I'd be interested to take this conversation a bit further forward after the meeting to see what the people in the data assimilation community really want to understand in terms of these error correlation length scales. Probably they're not constant. They certainly differ between sensors. They'll differ between different types of retrievals, and they're probably state dependent as well. And so there's a lot you could get into. Probably that's not required initially, but having some understanding from the SST side of what those length scales are may be useful. That was my comment. Thank you.
Thank you. Comments? Yes.
So if the information is in the atmosphere, does that mean that if you do direct radiant assimilation, you would have a better handle on this, do you think?
You mean the surface sensitive radiances in
Yeah.
the atmosphere?
So, as Chris said, it's a matter of the decorrelation length scales in the atmosphere. And so if you do radiant assimilation rather than using observations as in retrievals, then you have a chance of getting a handle on that because you would know the background error in the atmospheric information. So you might have a handle on that, or do you not think you would have a handle on that? Is the information good enough?
Yes, I think that it's this case of assimilation of surface sensitive radiances. It's a first example when it comes in mind when we talk about coupled assimilation. This information is directly transferred to the atmosphere, and we hope this will really improve the quality of our analysis, our forecasts by using this.
Okay. Another thing regarding the thinning at 50 kilometers, and also the fact that you do a median. I presume you use therefore a spatial observation operator to locate that particular observation that gets into. It's not just like a regular grid, right? It's actually correctly located within the 50-kilometer thinning. Do you see what I'm saying?
Well, yes, we all the time look for observations that are situated within this grid cell.
Yes.
And then we look we just check the values of these observations available, and we choose the median value.
Yeah,
so it's not.
But you apply the position of that median value.
The position can be different.
Yes, but I mean it's not centered is what I'm getting at.
Not centered.
Okay.
Not centered.
Okay. Right. One other thing is obviously with 50 kilometers, and particularly when you're at high latitudes, your Rossby radius is much shorter than 50 kilometers. It's 20 kilometers at mid latitudes, and you can have Rossby radius of 5 kilometers or less in the Arctic. So you're relying on getting spatial information from your model much more than your observations. Is that a fair statement?
Well, I don't know. I'm not sure about the Rossby radius, which is important in this case. But what is really important in the data assimilation is the correlation length scale that is imposed. It's also 50 kilometers, which is somehow corresponds to the thinning spacing. Well, but okay, I don't know what happens in up to the north when the Rossby radius becomes smaller.
Well, yeah,
I don't want to speculate on that.
Because you had a grid that was 5 kilometers for the local, is that right? 5 kilometers for the local assimilation, and I can't remember what the other scale was, but if you're going to fit at 50 kilometers, then the vast majority information within that 5 kilometer grid is not coming from the observation. So it's got to be coming from, is the ocean model itself 5 kilometers or in the regional model or not?
Yes, Greg?
Yeah, if I might jump on this. So I'm Greg Smith, Environment Canada. So I work with Sergey and Mark. So we also have a data assimilation system that assimilates the L4 SST analysis that Sergey was talking about. But in addition to that, it also assimilates sea level anomaly, in situ temperature and salinity profiles, et cetera. So in particular, when we assimilate the SST, we do it using fairly long covariances. And so it'll constrain generally the larger scales present in the system, whereas the scales around the Rossby radius, so the mesoscale circulation, is constrained rather by the altimetry. And we've done some tests, some observing system experiments where we withhold different information. And for example, compared to a free run that assimilates nothing, when we assimilate only SST, then in terms of eddy statistics in the system, we do get a very small gain for larger eddies, but we don't really constrain very well the mesoscale at all. For that, we need the altimetry.
Okay, so I mean, obviously the single, maybe SWOT is going to make a difference to you, and you'll find out a lot. I mean, have you had are you hoping to get something out of SWOT for that?
Yeah, so when we assimilate the altimetry, we can constrain the mesoscale quite well, at least for, so I guess to the larger side of the mesoscale. So we have a global quarter degree system that's only eddy permitting, so it only does so well. But then we have a regional system that's more eddy resolving, that's at a kind of 6 to 8 kilometer scale. And indeed, when we've done some tests assimilating the short period of SWOT data that's available, and it does show significant benefits in terms of the skill of constraining the sea surface height. And in some observing system synthetic experiments, then we find that we also constrain get a better constraint on the surface currents.
Okay, I mean, one of the things that I've seen with the West Coast ocean forecasting system that NOAA put in place is that they have this tendency, and quite a lot of people have this tendency, to validate against the satellite, which is what they tend to call it, which is kind of an interesting concept. Like, did we put our eddies in the right place? Let's look at what the satellite SST field is actually showing up. Generally, a high resolution SST analysis, like 5 kilometer. or something like that. So it's kind of curious that, is it just that it just doesn't like the information, or is it that it's too thin? I'm trying to, I mean, I guess when you take in the, presuming you're talking about the 0.1 degree CMC analysis,
Correct.
you don't thin that at all either? You put it straight in, or what do you do?
So we thin it. I think we take 1 point out of 3, or more than that, perhaps. And then we actually Shapiro filter the model fields. So we smooth the model fields to the same variance level as the L4 observations. And so that's in part why I say that we really just use it to constrain the larger scales.
Okay, right. That's not exactly chicken and egg, but now I understand. Okay, so switching completely now, unless anybody wants to, does anyone want to say anything more about thinning? Anybody else? No. One of the things I really like about the idea of coupled assimilation, and particularly the sea ice discussion, was that we don't know what the SST is under sea ice. So if you've got an actual ice model that's doing ice formation, brine rejection, and all those other things, you can actually, in that model, presumably have an under ice temperature, which we can use. But of course, you only get a good, result in the marginal ice zone if you've got accurate SST observations next to it. So it's a very symbiotic relationship there, I see. How do you feel about your under ice temperatures in your sea ice modeling? Do you think, yes, we should definitely all be using them because they're going to be better than climatological salinity and ice concentration, or what would you say?
I mean, I think it's still a bit of an open question. I mean, there are obviously a lot of significant uncertainties with respect to the sea surface salinities. I'm more familiar with the Arctic, so I mean, in particular, the amount of freshwater runoff, glacier melt, P-E, et cetera, is all very uncertain. Yeah. Snow on ice and these sorts of things. So that being said, there was a study last year by a group in Europe looking at intercomparing salinities in different models, and I think the outcome from that was that the salinities aren't as uncertain as we may have feared. Right. So I think that's not too bad. But then again, I mean, I think there are a lot of very subtle processes that you allude to about the brine rejection and whatnot, which will affect the freezing temperatures and thus these surface temperatures.
Right. Yeah. I mean, because if we look at global SST analyses produced by various centers, they tend to agree rather well everywhere apart from the Arctic, where the errors just shoot up tremendously, and particularly near the ice edge. And so it's something to do with the sea ice mask, probably. But then once you get under the ice, they all sort of converge again to being quite well agreed, because, if it's 100% ice cover, you're basically saying it's going to be minus 1.8, give or take a couple of tenths, roughly. So they all agree there. But it's kind of ironic that right where you'd really want to know how good it is, it's really quite a struggle, I think. So I'm kind of interested to see if we can sort of narrow that gap, especially as, the Arctic is, amplification and all that, and there's a real dynamic area for change at the moment, and an area of concern. So I'm very interested to see what can be done. I quite like the idea of using was it 1 kilometer SAR? Is that what you were? Was that 1 kilometer SAR product? I mean, because there's cloud and stuff up there, so it's very useful to have something at that sort of resolution near the ice edge as well. Yeah.
I might respond to that. I mean, I think one of the major gaps in the global ocean observing system, in my opinion, is the lack of Argo data in the Arctic. So as much as it's described as a global array, it really has some significant gaps under the sea ice. And I think there is hope in terms of getting additional Argo or Argo type profiling floats under the sea ice, which would then provide us some of these near surface salinities, which could help to constrain this very significant gap.
I mean, obviously, the trouble with Argo is you don't want it to bump its head, do you, on the ice? So I guess that you need something to constrain it, to stop it actually. Of course, if it doesn't surface, then it can't give you the data either. That's a tricky one.
But there
I
are
don't know.
the latest Argo floats, I think, have detection
Right,
algorithms,
yeah.
or there are versions that do.
Right.
And so that you can deploy them in the open waters in the summer and then
Yeah,
allow them
safely,
to reside
yeah.
under the ice during the winter. And given the larger areas of open water that we've seen in the Arctic in recent years, I think it does make the case for having additional Argo float deployments in the Arctic.
Sort of a handy side benefit, which you're not going to broadcast too widely. Okay, thanks.
We have a comment online from Philip.
So yeah, can I come in on that, on the under ice temperatures? So we have a new system which we're producing at ECMWF. We've started to produce an ocean sea ice reanalysis with a new, more up-to-date sea ice model. And one thing that we found was to make the assimilation work well, we had to introduce sea ice and upper ocean temperature balances. So basically, because if the SST was too warm, the model just could not support having ice sitting on top of it. So we had to introduce some balances to get the sea ice fields to look as the satellites were suggesting they should look. And so we're adjusting that under ice temperature, but we don't have verification of those temperatures. So I would suggest that these new ones are probably better than what we had before, but not verified. So if anyone can help verify that, that'd be particularly useful.
Any comments on that? No comments online. We have a link online. Maybe Peter can comment on that.
Yeah, hi. Sorry, Peter Galbraith. Yeah, it's just a link to Polar Argo, which basically are Argo floats designed, as Greg was saying, to be deployed under ice. And so they have transducer that detects ice and can abort the ascent and just go back down. They're used more so in the Southern Ocean. Very few have been deployed in the Arctic, but I guess it's something that will be happening more going forward. Thanks.
Thank you.
Okay. Is there any other questions or discussion points that anyone wants to bring up for this session? Online or in person, last call. Otherwise, we can break for lunch.